So in this video, we're going to deal with the slightly more general cases where the quadratic equation associated with the operator has complex roots. So in general, if you have an operator written in quadratic form with a constant coefficient, we can always complete the square, since it's a constant coefficient, in the following way. So like this, if you complete the square part, rest of the coefficients is whether either it's going to be a positive or negative. If it is positive, you can write it as a positive square. If it is negative number, you can write down negative times a perfect square. So if the negative case here, of course it factors nicely like this, d minus a plus bi, because this, if it is negative case, is a square minus a square, so you know how that factors. So that would be a minus b if you simplify it. It's like this. So it factors over the real coefficients. From there, these two operators commutes each other, and we can easily figure it out. These two are generated by these two exponential functions. C2e a minus bx. If you think about it, if b is not equal to 0, and if b is 0, and then in that case it looks like this, if you remember, c2 x times e to the ax. So in the real case it's all done, and what we're mainly dealing with here is a complex case where the sign there is a positive, so we actually have d minus a two operator done, and then plus b squared I. The special case in earlier video was with a equals 0 and b equals 1. That was a special case earlier. In this case, is a and b are kept in here. So we're basically going to go through the same method. I'm going to leave out some of the details to you, but I will give you the final answer. And of course, this is not the practical method, though the reason we're going through this method is that if one wants to see the existence and uniqueness of a second-order linear that has this situation here, and going through complex doesn't look like a proof unless one has that background of a complex analysis. So this can serve as a little rigorous approach to where the sine and cosine and e to the ax and those are kicking in, and we can actually rigorously derive and prove why they have to be the solutions. And that'll also explain the existence and uniqueness, and for this case as well. Okay, it's all about factorization. If you figure out how these things factors into a product of two linear first-order operator, and from there it's just an integrating factor technique. So I'm going to expand it back and solve for p and q like we did last time. So if you expand the first one, it's a d squared, and we can see it's negative 2ai kicks in, not I, is a d. And if you square that part, it's a squared, and the b squared, that goes in front of I. So that's, if you expand this operator, it looks like this. This is the coefficient of d, and that's the coefficient of q. And in our method, where sending q is the solution of the following differential equation, q prime plus a, which is negative 2a here, times q minus q squared equals b, which is a squared plus b squared. So that part here is a, coefficient of d, and that part here is a b, coefficient of I. The q, the second coefficient of a second factor, and it's going to be this q, and that's the solution of this equation. And p is simply this negative 2a minus q over there. So if you find the q first and then define p like that, and it's going to be factored nicely into d plus pxi, that's the second operator, and first operator, and appeared on the right, is d plus qxi, right? So we have to compute this q first. And a, since a and b are constants, this gives us a nice separable equation. So let's nicely separate this one here. That's q prime on the one side. The other side we have q squared, and plus 2a q and plus a squared plus b squared. So that's a quadratic in q. So before we actually divide both sides by this one so that we enter the separable equation, let me complete the square. From there we can do the substitution easily. If you complete the square, we have a squared in there and plus b squared out there. So these are numbers. Now finally, separable equation here, and it kicks in like this. Over there, here's a q prime, and down there is a q plus a squared plus b squared equals, you divide both sides by that quantity, so it's 1. So left hand side is purely in terms of q with q prime up there, so separable equation will work nicely. So here's the integral of 1 q plus a squared b squared q prime dx, which is qx dx, that's what that is. And if you integrate on the right hand side, you have x plus some constant you pick up in the c here. So this is the choice we're going to make, and q is supposed to be a solution. It doesn't have to be anything particular, anything that's simple, but we can change this number to get a different q that changes the q, so there's no uniquely way of factoring this quadratic, but there is a choice that you have to make over here. Now we're going to circle that choice that we're making here. Then we're going to come back if we have to make a different choice, but for convenience we can put c equals 0 and see what kind of simple solution you get for qx. So if c is 0, then the right hand side is just simply x. The left hand side is going to be in this symbolic way of integrating in qa. Now q becomes a dummy variable, squared, and here's a dq, right? This dx in the denominator cancel, and right hand side just become x there. And this is the typical arctan integration, shifted and scaled by something. So I'll skip the detail and just give you the answer to this part. So if you do that, it turns out, and this is going to be tangent inverse of q plus a is in there, and a negative 1 over b is the factor that makes this thing happen. You can check by differentiating this side in here whether this one is, you will get this inside of the integral back or not. So here on the right hand side is x. So you can start from here and choosing a different value. That will be x plus c, whatever you choose in here. But for now, this is the answer. So if you solve for q there, then you multiply b first, then that's going to be tangent inverse and 1 over b, q plus a, b times x. And apply tangent both sides. So if you apply tangent to that side, we have tangent bx appearing here, and this tangent on that side cancel. Now if you multiply b to that side and subtract a from both sides, and we have q equals negative a plus b times tangent bx. That's our qx there. So we figured out the qx, and the px is going to be, so over there, negative 2a minus q, so negative 2a there. And if you flip the sign, we have a positive a minus b tangent b. Bx is going to be the shape of p. So that's negative a still. And this time a negative b tangent bx. So let's put this thing together that we started at the beginning like this. D minus ai squared plus b squared I, which is, if you expand it, you have d squared minus 2a d plus a squared plus b squared I. That's kind of standard form in of this quadratic operator. And we're claiming that here's a d plus px, and px looked like this. So I'm going to write it negative a plus b tangent bx I, and here's d me pull out the negative, then it's going to be a minus b tangent bx there, an I in there. So it's actually meaningful and fun to actually check if it actually expands to this thing that's actually worth things to do. So that's what we'll do. We're going to verify our answers. So I put things up there. So how is going to actually expand? Let's verify our result. So you have these two things. It's clear that sum of these, first we're going to add this coefficient of I. If you add these two things, you clearly get 2a back. That's d. And negative b tangent bx and positive b tangent bx, they cancel. And second part is more complicated. This is the whole q, so we're going to differentiate this one, and a is a constant. So we have a positive b, and you differentiate that one, becomes a secant squared bx. By chain rule, we have to multiply the derivative of bx in there. So it's going to be b, and that would be the q prime part, and this will be p, the product of p and q. So if you multiply these two, the negative negative cancels, so you only get a plus b of that and a minus b of that. So we have, if you multiply, you get a squared minus b squared tangent squared bx I. So this is the q prime part, and that's a p times q part. That's how this thing expands, if this is px and that's qx there. Then if you just look at this part, I think it's clear that you have b squared and a squared. There's a squared and b squared is common. If you factor it out, you have a secant squared bx minus tangent squared bx in there. So it's a well-known identity that becomes 1. So we prove that it's a squared plus b squared. So that verifies that the coefficient of d is negative 2a. The coefficient of I part here is a squared plus b squared, so it recovers this one. So our factorization is correct. So if you look at this factorization, and if you want to solve this equation, the homogeneous equation, which is the same as the kernel of this whole thing, one of the parts of the kernel of this whole quadratic operator is coming from the first kernel of the first linear part. Once it's a 0, going through another linear is automatically 0. So what's on the right, it gives us a clue on what kind of solutions we're looking at. But you can't just take the kernel of this one 0. I think we talked about in an earlier video. These two things don't commute. So if you choose a function that is a kernel of this operator, and it has to go through from the right, it go through, and here is messed up and not necessarily annihilated by this factor. So it's easy to see we get something by looking at this kernel, but not by looking at that kernel. That'll only give you one function in here. And how do we see the other function kicks in, which is sine x, sine bx, and cosine bx in that shape? Is that going back and choosing the different c value? So we're back to this slide again where we made this decision to do this part 0. And of course there are many different choices we can make, c equals 1 and whatever, but there's one special choice of c that's going to switch this function to something familiar and give us another pair of another generator of the solution that we're familiar with, which is switching this tangent to cotangent by sticking in pi over 2 here. So I think that can be obtained by putting this c equals pi over 2b, I think. I hope that's right. So if I have c instead of 0, if I have pi over 2b here, I'm going to have pi over 2b instead of 0 there. So we have pi over 2b is added to that factor. So when you go to the next part, we're going to multiply an b in there. So that b's cancel. So we have now what I wanted, pi over 2 in there. Once you have this pi over 2 added here, then you will have pi over 2 inside, pi over 2. and you will have bx plus pi over 2. Then it's going to go, and we're here, I moved up slightly, and all the way this tangent bx, what we have in there, instead of tangent bx, we're going to have a bx plus pi over 2 and bx plus pi over 2 as well. So that part is also replaced by bx plus pi over 2. So what is this tangent bx plus pi over 2? If you go, tangent is a slope, so if you go pi over 2, the slope of this bx angle and pi over 2 is a perpendicular, so it's negative reciprocal. So you can easily predict what happens. So what we're doing is over here, and this is one factorization. I'm going to put the bullet mark there. This is one factorization. And second factorization, by choosing a different value, so there's no unique factorization, is that we have d minus a plus b times tangent of bx plus pi over 2. Let me write that down. Then I'll change it later. And we have the same thing, so I'm going to copy down quickly. So this is what we have, and instead of bx, and we have a bx plus pi over 2. What happened if you add pi over 2 inside a tangent? It becomes a negative cotangent. It's a negative reciprocal, and get the negative sign. So let me write that down underneath it. Right, I wrote it here. So this is what we have. We have one factorization with tangent in there with a negative sign in front of it, and another factorization, and we have on the right, we have cotangent bx with a positive factorization. So if you look at the kernel of this first order here, we pick up another solutions. So let me write that down all together up there. So here I collected, let me adjust the pad a little bit. I think I have it now. So by just choosing a different value, this came from c equals 0. The colors mixed up, and this came from choosing c equals pi over 2b. Then we can pick this handsome, very similar looking shape in the first factor on the right. So if you look at the kernel of here, we get one solution of this homogeneous equation associated with this operator. If you look at this first order equation, you'll get a different. So this is simply going through this integrating factor problem. So I'm going to look at first the kernel of that factor over there here. So if it's 0 already in the first operator, and second operator it's again guaranteed to be 0. So this is inside the kernel of the second order operator. So this is a first order homogeneous equation. You go through the integrating factor. Turns out it's simply e to the, let me erase it, here's a c1 times e to the ax. That's the integrating factor of that part. This part turns out, after you go through all that, it picks up cosine bx, where c1 is real numbers. So that's something we pick up. In the second part, if you look at the second factorization, we pick up this factor in here. So let's write that down. So the kernel of this factor in here, and it turns out, if you do these integrating factors, turns out it picks up c2 e to the ax sine bx is there, where c2 is real numbers. So as long as these two solutions are linearly independent, that's going to make this the full solution, the general solutions of this order 2 equations. So when is this two things are linearly independent? As long as b is non-zero, you can use the Wronskian, or there's two functions you can test whether it's a constant multiple of each other. So as long as b is non-zero, that means you really do have this imaginary part in this when you solve this equation, not this part being 0, then these two are really linearly independent. Therefore, the kernel of that order 2 equation that's written down here is really generated by these two functions, e to the ax and cosine bx. That came from this part on here, since they're linearly independent, and that second part becomes a second generator. This is quite similar to what you get from the complex numbers, and that's how I organize these find the right value the C1 sees here so that we matches it. If you choose it wrong values here, you will end up an ugly, different looking expression, but there as a collection is going to be the same collection. So we get this set of solution, and this is exactly what you get from the complex numbers. And instead, we kind of rigorously show that how it arises in this form. So this looks like a proof to us. But in practice, if you have to just calculate quickly, then using the complex numbers is the best one.